So good morning everyone. So I hope all of you had a great Deepavali yesterday. So let's continue with our next topic within the FIR filter designing. In our last class, I had discussed about the different designing methods. So over here we have discussed about the Fourier series method without using window, Fourier series method using window, then Fourier transform method without using window, and lastly Fourier transform method using window. Okay. So if you see, these two are uh, similar, whereas the next two they are also similar. The only thing is that uh, in the second and the fourth positions, what we are doing is that we are using some window functions to modulate the response of the filter. Okay. So these windows, as I told you earlier also, that they help us in reducing the Gibbs phenomena significantly. Okay, and that is the only reason why we want to use the windows. So why, how it is reducing the Gibbs phenomena? That is the important thing. We need to remember the fact that when we are discussing about the desired frequency response, which we have discussed it over here. If you see over here, we are having brick-like structures, right? So there is a sudden decrease or sudden increase in the response. Okay, so we do not want that. So the using of the windows, it allows us to design a filter whose these transition periods, they increase gradually and also they decrease gradually. When this happens, when there is a gradual increase or a gradual decrease in the amplitude response of the filters, the Gibbs phenomena is automatically reduced significantly. Obviously there might be some ripples either in the pass band or in the stop band. So those ripples, they are accepted. However, the Gibbs phenomena, it will be taken care of to a maximum extent. Okay. So today we will be discussing mostly about the Fourier series method using without using the window. Okay. The reason being, this is one of the easiest thing, and once you understand this, the the understanding of the other these three filters, they become easier, and all these three filters we'll be discussing tomorrow. Okay. So coming to the this algorithm, how you want to design a window using the Fourier series method without using the window. Okay. So let us take the example of a low pass filter. So the first thing is, draw the frequency response. Okay, draw the frequency response. So in our last class I have told you how you can draw the frequency responses of different filters including the low pass filter. If you see, in this first case of the low pass filter, the limit is varying from 0 to 2 pi. Okay, and now what is happening? The pass band is in the region of 0 to omega c and 2 pi minus omega c to 2 pi. Okay. On the contrary, in the second case, the same thing, when we represent it in the minus pi to pi region, we saw that the limit, it changes from minus omega c to omega c. What is the reason? We have discussed previously that the frequency responses, they repeat itself after 0 to 2 pi region. Okay, so even in the negative region there will be a repetition of the frequency response of the filters. Okay, so that means this band, what is 2 pi? 2 pi is basically 0. So 2 pi minus omega c. Yeah, so if we replace 0 with the 2 pi, because 0 and 2 pi are similar, so we get minus omega c. So you see, it becomes minus of omega c to omega c. So our limit becomes minus omega c to omega c. Okay. So the first and foremost thing is to, depending upon what type of filter it has been mentioned, you need to draw the frequency response of the filter. Okay, you need to draw the frequency response of the filter. Once you have drawn the frequency response of the filter, we have to calculate the impulse response Hn. Okay. Now, what is impulse response? We have again discussed. Suppose we have a system Hz. So, if we give delta n as the input xn, then we get Hn, which would be basically the Yn when we have given xn as the delta n. And accordingly, for this delta, for this Hn, we will be getting a series of sequences. Since we are talking about the FIR filters, this sequence, it would be time limited. Are you getting my point? Now the question is, from the frequency response, how do we get the Hn? Okay, so the Hn is given by 1 by 2 pi integral of minus omega c to omega c. Okay, usually the limit should have been minus pi to pi. Okay, so for the generalized case, whether it is a band pass filter or it is a band reject filter or high pass filter, the limit is always minus pi to pi. However, in the case of low pass filter, we have just seen that the passband filter, it is present only within the region of minus of omega c to omega c. Hence, this minus pi, it is being replaced with omega c, and this pi, it is replaced with the omega c, because outside this minus omega c to omega c, the frequency response, it comes out to be 0. Okay, so after we have fixed this limit, we have h of omega e to the power j omega n d omega. Okay. However, in our last class, we have discussed that modulus of h omega is what? Modulus of h omega is 1. Right? We have already discussed. So, this equation Hn, it becomes Hn equals to 1 by 2 pi integral of minus omega c to omega c e to the power j omega n d omega. Okay. Now, when we try to calculate Hn, as I told you, you will be getting a series of sequences Hn. Here, if you see, the n is equal to capital N. Now, this capital N will decide the order of the filter. So, suppose the order of the filter is 10, because you will be given with the order of the filter. So, if the order of the filter is 10, then you have to keep it in mind that you have to find out the values of Hn in the region of H0 to H of capital N. Okay. In some cases, as I told you in our last class also, that instead of order of the filter, you may be given with the length of the filter, where length is equal to capital N plus 1. Okay. Now, once you have got this h of n, determining the transfer function, it becomes quite easy. Why? Because I have already told you, suppose you are having a series of number h0, h1, h2, h3 and so on. So, transforming it into the z transform, it would be h0 into z to the power minus 0 plus h of 1 into z to the power minus 1 plus h of 2 into into z to the power minus 2 plus h3 z to the power minus 3. Okay. So, what is this? When this z component comes, So it becomes Hz. So previous one it was Hn. So we can easily perform the Z transform and we can find out the transfer function of the system very easily. Okay. Now once that is done, then we can go for the realization of the filter. We can go for the realization of the filter. Okay. So this is the whole process. So again, if we talk about high pass filter, only this limit changes. This limit over here, this changes. Okay. If it is a band reject filter, again this limit would change. Okay. Now next, let us take an example. then पानी का बोतल नहीं लाएगा थोड़ा देखो. So design an ideal low pass filter with a frequency response. Okay. So what is the frequency response? Frequency response is given by Hd e to the power j omega. It is equal to 1 in the region of 0 modulus of omega pi by 2 and 0 otherwise. Okay. So what is this mean? This means this Hd omega, it is having a passband filter in the region of minus pi by 2 to pi, right? Modulus of omega, because we are having modulus of omega. So modulus of omega means again minus omega, both minus omega and plus omega they will be covered. So minus pi by 2 to pi by 2. Okay. So we have drawn the frequency response of the filter. Now find out the HDN or the HN. HDN, D means desired frequency response. Okay. So HDN, or you can also in simpler term at this moment we can call it as HN. It is equal to 1 by 2 pi minus of integral of minus pi by 2 to pi by 2 it is for j omega and d omega. Then just solve it. If you do the integration of this one, you get 1 by 2 pi, it was common. Then this jn, because d omega is the operator, this jn, it comes to the denominator. Then it is called j omega n in the range of minus pi by 2 to pi by 2. Okay. So we get this thing. Okay. Next word, 1 by pi n e to the power j pi j pi by 2 n minus of e to the power minus j pi by 2 n divided by this 2j, we can take it inside. Okay. So when you do this, what is this fraction? If you see e to the power j theta minus of e to the power minus j 2 theta minus j theta, it is equal to 2j sin theta. So if you take this 2j in the denominator, we are getting basically this thing. So what is this? This is nothing but the sin theta. And what is the theta? Theta is pi by 2 n. So sin of pi by 2 n divided by this pi n, it comes over here. Okay. Now we have discussed that over here find the values of Hn for L equals to 11. Okay. What is this L means? N plus 1 equals to 11, that means n equals to 0. Okay. Now here your L is equal to 11. So what we will be doing? HDN, it should be sin of pi by 2 n divided by pi n for modulus of small n less than equal to 5. Okay. So how did you get this less than equal to 5? Capital N by 2. Okay. So when length is 11, so it is basically type 1 filter, right? So herein what we are doing, when we are doing this, we are basically saying at n equals to 0 we will be having a value, and then will be having some values like this. So this is the origin, 1, 2, minus 1, minus 2. So across this origin the values will be same. Okay. So 0 for the other cases. Now when n is equal to 0, what happens? If you look over here, if n is equal to 0, if you put n equals to 0 and 0 over here, then this becomes infinity. So accordingly we have to apply the L'Hospital's rule. So wherein it says that limit n tending to 0 sin of pi by 2 n divided by pi n, इसको हमें we have to convert it into this format, limit theta tending to 0 sin theta by theta, it would be equals to 1. Okay, so we have to convert this in this format. So if you see sin of pi by 2 n divided by pi n, it is given, but in the theta we are having pi by 2, so we have to divide both this denominator by multiplied by 2 and divide by 2. Okay, so if you take this, we get this half, half comes out, and we get limit n tending to 0 sin of pi by 2 n divided by pi by 2 n. So this fraction, just now we have seen that it is 1 as per the L'Hospital's rule, and we get half. Okay, now if you see over here, for n equals to 1, we have written hd1 equals to hd of minus of 1. Okay, hd of minus of 1. So we are having sin of pi by 2 by pi. Why I have written hd1 equals to hd minus 1? If you see over here, I have shown you, we have taken this filter values across the origin. Okay, across the origin. And what is the x-axis over here? Can you tell me what is the x-axis? Yeah, x-axis is n equals to 0, 1, 2, 3. And what is the y-axis? Y-axis is the amplitude. Okay, so we have hd1 equals to hd of minus 1 sin of pi by 2 by pi, and it comes out to be 1 by pi. So we will limit ourselves to 2 digits after the decimal points. So please keep it in mind. Okay, otherwise every one of you will be getting different results, and then checking the copy, it becomes a bit tricky. Okay, so then n by n equals to 2. If you put the value, you will get 0. N equals to 3 minus of 0.111. N equals to 4, it is 0. N equals to 5, it is 0.06. Okay, now after you have got all these things, if you see in the previous case, we have started with minus n and we have gone into plus n. So what we need to do, we need to shift these values towards the right, so that the last value, in this case the last value is this one, where n is equal to minus of 2, it now comes to the origin. Okay, now why we want to do this? Because if you look into the previous case, we are taking negative n values. That means what is happening? We are taking the past values, but filters, they should be designed with n values greater than equal to 0. However, we have done that for the sake of easy calculation of the parameters. Okay, for the sake of easy calculation of the parameters. Otherwise, you would have to calculate all the frequency, all these HD values from 0 to say 11, right? 0 to 11 hn. So this is the thing, h of z is equal to z to the power minus l minus 1 by 2, okay. Then summation of n equals to 1 to l minus 1 by 2 h of n multiplied by zn plus z to the power minus n, and then separately we are having h0, okay. So if you see z to the power minus 5 multiplied by 0 z to the power minus 5, it comes to the middle point, okay. Another important thing it is to be remembered is that when we talked about the realization of the filter, we talked about that we can only implement delays. We cannot implement or introduce Z in the realization of the structure. However, if you take the case of the in the previous case over here, since we are having the minus n value, so something of Z of minus n, it would become Z of n. So the realization of this one is not possible, okay, and hence we have to make the hn a right-handed signal, okay. And this is the equation how you uh, what do you call, convert the hdn sequence into a right-handed sequence, okay. Then after that you get hz and just put up the values and you'll be getting the transfer function, okay. Then coming to the ideal high pass filter, again the same thing. So if you see 1 modulus of omega in the region of pi by 4 to pi, and in the other regions it should be 0. Again L is equal to 11, find hz. So if you see, this is the frequency response of our high pass filter. Again if you see 1 by 2 pi, the same equation, but herein both the pass bands they are separately present, whereas in the previous case it was conjoined, the negative half and the positive frequency component they were conjoined, so we had only one integral. However, herein we will be having two integrals, okay, but the process remains the same. You perform this, you get this hdn equals to 1 by pi n within bracket sine of pi n minus of sine of pi by 4 n for modulus of n less than equal to 5. That means again over here what we are doing, we are calculating, because L is equal to 5, so we are calculating the hn values for n equals to minus 5 to plus 5, right. Now again here for the first case you have to put the limit, this limit of n tending to 0, pi of n to n, and this thing. So you calculate this, it comes out to 0.75 n, and the rest of the things they are pretty easy, I suppose all of you will be able to do it. Just you have to put the values. Since you are having pi, please be reminded while calculating the coefficients, your calculator should be in the radian mode, okay, not in the degree mode. Otherwise, your calculation will be incorrect. If you want to work with the degree mode, then you have to convert this pi into the degree. So after you have calculated all this thing, again shifting of the hn values to make the hn a right-handed signal, and after that this is the filter transfer function of the filter. Then ideal band pass filter, again pi by 4 into 3 pi by 4, you draw the frequency response, you see the frequency responses. So again there will be two pass bands, so there will be again two integrals, again in the same thing. You will be able to, you should be able to calculate all these parameters, and after calculating this you will be getting the exact values. Now let us take this example, because it is the simplest one. So over here you will see there are a lot of complex values. However, in this idea, ideal band pass filter, we are having just a handful of this complex values. So it is easier. It would be easier for us to work with this one. Okay. So herein we are given with this HZ value. Okay. Now if I ask you, you try to find out the amplitude response and the phase response. What I said previously, Z equals to e to the power j omega, right? Just replace this in all these equations. Instead of Z, we replace those things. So it is so your hz at z equals to e to the power j omega, it becomes 0.5 e to the power minus j 5 omega. Okay, minus 5 was already there, so rest would be e to the power j omega, and accordingly you put the values of z everywhere. Okay, so you get this function, right? Now once you have done this, so what we have, it is about j omega, it is basically nothing but cos of omega plus j of sin omega, right? Again you start putting it in this equation and you get this equation. Now what do? You open up all the things. After opening up all the things, you will be getting some real components and some complex components. You bring them together, and once you bring them together, it is in the form of a plus jb. Okay, it is in the form of a plus jb. So at whatever frequency you want to find out the amplitude response, you just put the values of this omega. So you will be getting the values of A at that omega, values of B at that omega, right? Now, once you have got A and B for that thing, you get modulus of H, which is would be equals to under root of A square plus B square, and phase of H omega, it would be tan inverse of B by A. And how you should calculate, I have already given you in the previous in one of the previous classes. This is the chart which you should remember. Where is that chart as well? Anyway, you must be having that chart. I'm getting that. The one of the previous classes I have given you the chart. So please look into that. Okay. So herein you have been given with some examples at omega equals to 0 degree. So you find out all these things. Then omega at omega pi by 4, you find and calculate all these things, and then again at pi by 2, 3 pi by 4, and pi. So you have to calculate all these values. Okay. Then lastly, for today's the same low pass filter example or any other filter example, you may be given with this kind of specifications. Okay. So cutoff frequency 500 hertz, sampling frequency 2000 hertz, order of the filter 10, length of the filter 11. Okay. So in this case, the first step would be to normalize the cutoff frequency. So when you normalize the cutoff frequency, omega c equals to 2 pi fc by fs, which is equal to 2 pi 500 by 2000, which gives us pi by 2. It is a low pass filter. It is a low pass filter, right? Now from here you get the transfer function. Now if we look into this transfer function and the transfer function we have been discussing over here, they are same. Okay, the same equation or the same numerical, just by tweaking the question we can uh, create a new type of numerical, and we need to do this. Okay, so with this I will stop over here. Since this is the first class with our this filter, I would urge you to practice this within the class, and if you are having any problem, then we can discuss it. Okay, anyone has any problems anywhere? No.